In the table 1, we will have the operation conditions. Okay. Mention that the standard deviation is 21 previous observation and is 3.8. Okay. The first fraction is implemented with these generators. And with that, we are going to make the X matrix, and we also have to do a second fraction. Okay. So here we have the matrix design for the first and second fraction. So as you can see here, we have the confusions of these generators that you get it like, I don't know, if you use the 1. Here you have the 1, so you delete it, so you have 2 5. In this case, the same, and the same in this. So that it will be the confusion of the variable 1. It will be the interaction between the variable 2 and 5, 3 and 6, and 1, 3 and 4. Okay, and that is with all the variables. So we have the 2 here. It will be just 1 and 5. In this case, we don't have the 2, so we have to put it in there. The same in the last one. Okay.
Sorry. You have to the batteries 2 in the 1 to 6.
Yes, if you don't have the 2 inside the generator, you have to put it in the confusion.
Oh, okay.
So the same with the 3. So here we don't have the 3, so we have to
1 to 5.
put it inside. In this case we have it, and in this case we have it. And then with all the confusions. So the confusions that are important are we need to have the variables like alone. In this case, we have the matrix design for the Y, the A, and 1, 2, and 3. So we have to make like a model that it will be something like that. It will have the first variable, the second variable, and the third one. And the confusions. So we have 1 with 2, 1 with 3, and 2 with 3, and 1, 2, and 3. Okay? So these confusions or these interactions must be connected to the other variables. As you can see here, we have 6 variables that can be significant for the current drive. Okay, so we have 6, and here we have 3. So this interaction must be connected from one of the other variables. Okay, so how you see that? With the part of the confusions. As we see here, we have the 1, the 2, and 3. Then, if we saw the variable 5, you can see it's connected with the interaction 1 and 2. The same with the 6, it's connected to the interaction 1 and 3. Okay, and the 4 is connected with the 1, 2, 3 interaction. Okay, and here we have the interaction 2, 3 is the same as 1, 4. Okay, so that is the most important part to get start with everything. So this is the same that I made here. You think in a value for the first part and then use it for the generators. You can also connect the generators. For example, this one and this one, it will be something like that. This one and this one, it will be that. This one and this one, it will be that. And then you can also connect that connections. For example, this and this, it will be 2 or 6. And that is the same, okay? So that is the idea, because with that connections, you can also get the confusion of the variables, okay? But the most important part is the first one, okay? So, we have that in generators, and we have also the second matrix with this generator. As you can see, it's almost the same, but here you have a negative value. Okay? So, the difference between the first one and the second fraction, it will be that here 5 is connected with less 1, 2. Okay? And the same for the 6. So in the part we are going to make the matrix, we may use the negative value. Okay? So, to get to this, we have this, okay, the sign matrix for the first fraction, all of that I put it in here. This will be the first fraction. So, you can make the model that, as I said, it will be this model. We have to get the interaction of 1 and 2 is just multiply the 1 and 2. And the same with the other. And here you can use the 1, 2, and 3, or use the 1, 2 with the 3, or whatever you want. But you must have the 3 values. Okay? So there we have the fraction 1. So we have to do the same with the second one. As I said, we have here the negative 1, 2. And this one is negative 2. So, in this case, it will be the same, but with a negative for the 1 and 2. And here is 2 negative 4. And this is equal. Always the most important in this type of design is the variable alone. Then the second, like the interaction between two variables. And the lower important is when you have 3 or more variables. Okay? So, here we have the matrix X for the both generators. That it will be the same as this one. It's just this. Without the B. Important that in the both cases the value of the cost per ton are different. Okay? So we have different experiments. So also we have to use this value. This is equal for the both fractions. Okay, it will be always like that. If I don't remember that, I right? I think this is like the standard. It will be an inverse, a move, transpose, this extraction with the extraction. As you can see here, we have this value that, if I am not wrong, yes. So we have here, we have 8 parameters. So in these cases, the Tx matrix, it will be always 1 above the value of parameters. Okay, and it's always like that. Just this part with values and the other part with zeros. And this one, it will be get the same value. Okay, because have the 8 parameters. So we will do inverse. Transpose. I don't know why is there an error, but it's this thing. Okay, so we are going just to use that. So to continue, we must get the parameters of each fraction. Here we have a mode of transpose, the X matrix, with the value of m1. And here we have the move. This is the same that as we were showing in the last assistantships. Okay. So we have to make the same for the other part. And here it will be this one and this one. So, here we have the parameter for the fraction 1 and the fraction 2. So we have each fraction is connected with each generator, okay? And with each y value, okay? So, as we get different parameters for the same model, we must make like a average and a difference between these ones. So we have to do this one plus this one above 2, and this one less this one above 2. Okay. So that it will be this one, and 2, and this one less this one about. So the idea of this part is because we have, as you can see here, if we make the sum because, between one fraction and the other fraction, you are going to have the parameter that is connected, the variable that is connected to that parameter. Okay? So, for the first fraction, we have this first value, the second value, sorry. The second value is connected to the 1, 2, 5, and 3, 6, as we saw here. And for the second fraction, it's the same but with the negative. So, if we assume that, we are going to have just the one value. Okay? So we have, as you can see here, you have 1 to 5, 3, 6, 1 less 2, 5 less 3, 6. So this are related. 1 plus 1 is 2. Above 2, it will be the 1. Okay? So it's the same for all the parameters. So you can see which variable is connected to that parameter. As you can see, the first parameter will be always the constant one. Then we have the variable 1, variable 2, 3, 5, and 6. And here you have the interaction between the second and the third one. And the last part, you are going to have the 4 connected to the interaction. But that interaction is not that important because it's the first one with 3 variables. So it's not that significant inside the variable. Okay? So, as we have the values of the sum and difference, we can get the interval of confidence to can tell if these values are or not significant. Okay, in this case we can use just the confidence interval because we have the pure error variation in the statement. If we don't have that, we must use the normal probability plot. In your assignment, I think you have to use that. It's the same development, but in this part I don't know. You get this, put it in the MATLAB, use the norm plot, and you are going to have the norm plot. And the values that are not connected, for example, I don't know, we are going to have something like that, for example, with the 0. And we have the values like that. We are going to have a line, something like this. The values that are not connected to the line, the ones that are not connected to the line, it will be significant. In the case we don't have the confidence interval. This is the norm. Plot. Okay? And with these values, you must get the pure error. Okay? In the case of this assignment. But in this case, we have the pure error, so we can get just the confidence interval. So, as we saw here, we have 3.8 standard deviation. So the variance, it will be 3.8 squared. This value will be just this one. The degree of freedom, it will be the 21 less 1. The value of t will be the point t of 1 less alpha above 2. with the degree of freedom for the pure error. Remember, always to have the pure error, use the pure error, not the residuals. Okay? So the confidence interval, the factor, it will be this t with the square root of the pure error variance with the value of this matrix. So this will be our Z. So to get used that, we are going to make this part. This is the same that you can make for the norm plot that I said. So you put here the fx. For the part of the sum, you use all of them less the constant one. Okay? And then you use all the fx for the difference part. Okay. Here just put the numbers. And here we are going to get like the distribution of the fx. So here we have the value of n less 0.5 above the maximum value, which is in this case 15. So we get that, and here we are going to sort the f to see which one has to be with the first value and like that. So here we have the distribution. As I said, in this case, here it will be this value. So the values that are above this confidence interval, it will be significant. So these 5 values, it will be significant, and all of these ones, it will be not significant. So we are going not to use them. So in this case, we have these ones. No, this one. These ones are the significant values. As we can saw, we have the 9.5, which is the parameter connected with the variable 1. This is the variable 1. The 9.878 with the variable 6. Yes. The 11 is connected to the variable 5. This one is connected with the variable 4, or with the interaction between the 3 variables. And this one, it will be the variable 2. So as you can see here, the variable 3 is not significant. So in the part we are going to, I don't know, like if you must analyze something, in this case, we must get the value of the minimized cost, and with these operation conditions, so which it will be the minimum operation. So in these both cases, we can't use the non-significant variables. Okay. this one are yes. This one is our significant parameters. So we are going to not use the 3 and the interaction 2 and 3. Okay. As I said, you can in the segment you are going to have something like this, but more close to the 0 because the values are in that case, and you are going to have a line like this. Okay, so the values that are connected to that line, you must use it for the period. And the values that are not connected to that line, you use it for the model. Okay. So, as we get the significant values, we can get the residuals. Okay, so we get that in this case, this one and this one are not significant. So when it's not significant, we are going to use a 0 in the beta. The same for that. We have another 0. Okay, so our E model, it will be the equation that is there, that is just, it will be the NMU between the x fraction 1 and with the beta value. And the residuals, it will be just the difference between the model and the measure. Okay. And the same for the second part. So here we have the model 2, that it will be the second matrix, but with the same beta. The same for the residuals. So here we have the residuals. We can tell our average is 0. We have normal data. We have a constant variance, and the independence is closer to less 0.4. Okay. So important when you get this in the assignment, when you get the analyzed for the residuals, to comment something about it, not just to put the values or the charts. It's important to tell, I don't know. Here we can see we have normal residuals, or here we can see that we have constant variance. So in this case, we pass the residual part, so we can go. You can make the ANOVA if you want. In this case, I am not going to do it because we know about it. If you want, I can do it. Okay? You can do this? No? Yes? Well, the ANOVAs we saw always. We get the regression part, the residual part, the error part, and the lack of T part. So the regression part is not that important. The most important part is the lack of fit. For the residuals, it will be the square. And the residuals is this. The degree of freedom of the residuals are the LSP. In this case is M, and the P are 8 parameters. Yes. And the MS is always the SS above the degree of freedom. For the Bureau, we have the MS is 14. The degree of freedom is 21 less 1. So the SS it will be the MS with the degree of freedom. Yes. And the lack of fit, it will be always the difference. Or in this case, we can get the difference. So in this case, you must do the same that you made in the assignment 3 or 4, I don't remember. But the F distribution. So it will be this one about this one. And the F distribution, it will be with this, the 8, the 20, and so we get lower than the 5, lower than the significant, so we can tell that we have no evidence for the lack of fit, if I am right. But that is the idea of Yanno. The same that you made with the assignment. So, as we saw, we get the analysis of the residuals, we get the analysis of the ANOVA, we can respond the questions that we have. The first question is, suggest how the drying process should be operated to minimize the cost per ton. So, how we can do that? If our, in this case, here is the cost per ton. So, if we want this value be the lower one, it's just here you have to get all negative values. That makes sense, because if you have a value here and you like rest all these values, you are going to get the minimum values that you can get. So we have these parameters which get these variables that get, in the case of one is significant, we get that significant if halves of but we get that the first one, this one is significant, so this, yes, and it's positive, the 9.5. The second is significant and is also positive. The third one is not significant and is negative. And this is significant. This and is positive. The 5 and 6 are significant and positive. So in this case, the third variable we are not to use it because it's not significant. As you can see here, this will be just like a 0 for that one. And as you can see, we have all the parameters that are connected to these variables are positive. So that means that we can that we must use this line. As you can see, all the parameters are negative. The first, because the other are connected. But important is to get all the variables negative to can reduce the cost. Yes, ¿se entiende? So that is the idea. It's the same if you have to maximize, but use the positive value. Okay. So if you have to minimize or maximize the value of your product, you must analyze the value of the parameters. And with that said, if you must use like the less one or the positive.
I want to ask, why are we?
And the lower values, it will get the negative one. Okay? So, here we have positive one, and here we have the negative one. Okay? So, if we use that information with the operating conditions, we can show that the corn feed flow rate is in the higher part. So here we have a positive one. Always in the constant is a positive one. So there is just a one. Then the initial corn moisture in 25, it will be the positive one. Here the third variable in our case is not significant, so we are just putting a 0. The corn type is in A, which is negative. The hot air flow rate is in the negative. And in this case also the interaction between the second and third one variable is not significant, so it's a 0. If it is significant, it's just make the one with the second. No. The second with the third. Like that. So it's 0 in this case. And the final one is in the positive one. So this that we get here, it will be our xk. Okay? So with that we can transpose it like that, and with that we can get this value that we see here, that it will be just between the xk with the matrix that we get here, with this one, and with the transpose one, like that. So here we have a value of 0.75. So the confidence interval for the y is the value of t that we get here, t, with the square root of this value with the variance of the pure error. So there we have the confidence interval, like the factor, the cost, like the model. In this case, it will be the MMO between this one with the betas that we get here. So our cost in this operation, it will be the 77.6, okay? But they are asking for the minimum operation. For that, we just we use the interval cost, interval confidence, sorry. So there we have just the cost less this factor value. And then we have the minimum cost for this operation conditions. Okay, that's important because if you just get like the cost with that values, it's not the minimum or the maximum, I don't know, whatever they are asking. You must use this confidence interval to can tell, as we saw in the other classes, we are going to have the value of y, right? But we can get the y inside all of these values with the interval of confidence. So if we get the interval of confidence and we can go for the lower part, for the minimum, until this value, it will be the minimum, and in this case cost per kilogram that we can have with that condition. Or is the maximum or the other side. Okay. Plus. And that is all. I don't know if there is some question or something that is not I don't know, some question or something. In the MATLAB you get the line, but you can tell. I think in the MATLAB this line is like too closer to one value. So there you must like analyze and justify if you get this value like significant or no, something like that. I don't know if it is like that actually, but there was one value that is too closer for the line that it's difficult to tell that is or it's not significant. So that is. You must stop. Okay. Then you get it with the pure error. You can tell that if it is or it's not like right.